Today we're going to use food coloring, water, and a candle to show how air pressure can actually force water up a column. It's a really simple experiment to do, but actually very impressive. All you'll need for this guy is some very simple things that you'll find from around the house. You'll need a plate, you'll need a candle, and you'll need some food coloring. It doesn't really matter what color food coloring you have, but I chose blue in this case. And then you'll need some water that you can pour, and then you'll need an empty glass. Now you're going to want to make sure that the glass is able to fit around your candle that you actually choose to use, and you'll see why that's important here in a minute. So what we're going to do is just move this guy over here, put the candle in the center, and then what we're going to do is pour some water into this plate. Now, how much water do you need? You really don't need a lot of water, but you want to go ahead and fill it up where you have a fair amount of water, something like this. All right, and then what you want to do is put this candle right inside like this, and of course you want to light the candle, and you want to get your permission from your parents for sure to do this, or an adult, and wear your safety glasses, because anytime we're working with candles or anything like that, we definitely want to be safe. So let's go ahead and light this candle. There we go. Let's let it go ahead and get nice and hot. Basically what's happening here, if you think about it, anytime you light a flame or light a candle, is the flame is starting to grow, and right above this candle is a pocket of air, a whole column of air right above the candle, and this column of air is starting to get hot, okay? So and that's going to be very important for this experiment here. Now the next thing we want to do, while the air is getting hot and while this candle is starting to work itself out, is we want to make this water colorful. The only reason we're doing this is so that we can see the water as it rises up into the glass. So what we're going to do is just put a nice bit of food coloring, probably too much food coloring, but we like food coloring, so that's okay. And just give it a nice gentle stir. Want to be careful not to make a mess here. But want to give a nice gentle stir, okay, so that it's a nice even blue color. So there should be absolutely no way that we would not be able to see this blue water as we do the experiment here. All right, so the next thing we're going to do is take our empty glass, which is the one that we have right here that fits over the candle. We're going to turn it over on top of the candle and push it all the way so that it's sitting inside this water. And I want you to look very, very carefully at the level of the water inside of this glass as this happens, okay? On the count of 3. 1, 2, and 3. Now let's watch carefully. So the candle is going, and the candle is using the oxygen inside of this guy here. It's heating up the air, and then eventually, because of the seal there, the oxygen is all being used up. And then what happens here, look what happens here. As the candle goes out, the water level is rising, rising, rising inside of that cup. And you can see the water level rose probably maybe 1.5 centimeters, something like that there. So this is a demonstration, again, in air pressure. I can go ahead and take my safety glasses off now that we've actually done the experiment. What's happening here is whenever we light the candle, we said more than once that it's heating the air up, right? And we already talked about in other experiments, when you heat things up like air, they want to expand, they want to get bigger, right? So the air that's sort of in this pocket around the candle, it's wanting to expand, it's wanting to get bigger, it's wanting to push away, right? And so when we cap off the top of it with the cup, we exhaust the oxygen supply. The candle can't burn anymore because there's no more oxygen inside. So slowly the candle flame goes out. Right? Now, as soon as the candle flame goes out, there's no more heat being produced inside of this guy. So the air that was left behind, the air tried to push its way away from the candle. Whatever air was left behind immediately starts to cool off, right? What happens to gases when they start to cool off? They start to get smaller. They start to contract, right? When things contract, we say they have lower pressure. When things expand, we say they have higher pressure. So what really happened here is we made the air hot so that when we capped it off and cooled off the air that was left behind, it starts to contract and the pressure inside of this glass gets lower. because of that. So what we have at the end of the day, once the candle goes out, is we have low pressure inside of this glass. And where's the other pressure at in this situation? We have higher pressure outside the glass because of the atmosphere. We don't feel that pressure, but it's always there. So we have so much pressure pushing on the water all around this glass. It's pushing down, that's atmospheric pressure. And then inside, we created a situation where we have low pressure. So we have a low pressure inside, which means low pushing, high pressure outside, which means higher pushing. So the outside air pressure pushes the water level down, up into the glass. It goes down around the bottom lip of the glass and goes up. And you can see it with the food coloring. The only reason that we used food coloring was so you could see it. So really you can do this experiment with a candle, a glass, and a plate and some water, and you don't even need the food coloring. That's just to help you, get a little bit of a kick out of seeing it rise. And you can see that it probably went up a good 1.5, almost 2 centimeters, something like that. So go grab an adult, go get the materials, and show yourself the power of air pressure, that it's pushing on us all the time. We create low pressure inside, high pressure outside, and that forces the water level up into the glass.
Learn anything at mathandscience.com.
Today we're going to do a really neat experiment. We're going to learn how to make a cloud inside of a 2-liter bottle of soda. It's really actually very impressive. It only takes a few materials that you can usually find from around the house, and it's a really great way to understand how clouds form and all of the things involved in cloud formation. Now, all you're going to need for this experiment is some rubbing alcohol. This is regular old rubbing alcohol that you can find from the drugstore. Some duct tape, you'll just need a little bit of it. You'll need an empty 2-liter bottle of soda that you've washed out and cleaned out. And you need some kind of bicycle pump. Now this particular bicycle pump is really big and bulky. If you have a smaller one, even one that might be used just to air up, basketballs or something, it usually will work just fine. So you need some kind of pump to do this experiment. Okay, the first thing you want to do is make sure you get permission from an adult to do this experiment, because we are using alcohol, household alcohol. So it's a chemical. We want to make sure we're asking for permission. We also want to make sure and use our safety goggles. So let's go ahead and put those on, our safety glasses. Now the next thing we're going to do is we're going to open our 2-liter bottle of soda, and we're going to pour just a little bit of the alcohol inside. Now how much doesn't really matter, but probably a couple teaspoons. Something on the order of a couple teaspoons. So let's go ahead and shut that off. We'll put the alcohol off to the side. And what I like to do is kind of close off the top after we've got the alcohol in there and just sort of rotate it around like this. And what you're doing is you're coating the inside of this plastic container with this alcohol. And also, if you've ever played with alcohol, you know that it kind of feels cold when you pour it on your skin. That's because the alcohol is evaporating. So what's happening inside of here is the alcohol is coating the inside of this container. It's also evaporating. So inside of the bottle here in the air is a little bits of alcohol molecules that are kind of going into a gas, basically. So they're kind of filling the air up in here with this alcohol molecules. And that's really important also for this. So we'll explain why that's important in a little bit. Now, ultimately, what we want to do is we want to take our bicycle pump and we want to be able to force air inside of this container. Now, you're going to have a different bicycle pump than the one I have. Mine has sort of like this plug at the end of it here that's almost the right size. It's almost the right size to fit in there, but not quite. So what I'm going to do to help me force air in there is I'm going to use a little bit of duct tape to sort of seal it up. Now yours is going to look a little bit different. Some of you might have a needle valve for like a basketball or something. In that case, I'd probably put a cork in the top, like a wine cork in here, and then force the needle through the cork to try to get a nice seal. You might have to play with that part of it to get exactly what you're looking for, but ultimately all you're trying to do is have some kind of a nice seal, a temporary seal. It doesn't have to be a crazy permanent seal, just some sort of temporary seal so that you can force this air, because we're going to use the air pump here to push a lot of air in here. So what we're going to do is just take our duct tape, for my particular pump anyway, and I'm just going to sort of go around here. It doesn't have to be perfect. I just want to get it nice like this. And obviously we've covered it, so we want to be able to get the air in there. So I want to put a hole right in the middle. I'm using a screwdriver bit to do that. You could use, a pencil or a pen or something just to kind of get the hole in there. All right, so now we have duct tape there that's going to hopefully help us seal this container. And then we have a bicycle pump. And then what we're going to do is basically hold it. I'm going to hold it there with my hands while I force air and while I manually pump it up. And then when we release the pressure, when I move my hand away, the air pressure inside that we've pushed in there is going to quickly escape through this hole. And if we've done it right, we're going to make not only a cloud in here, but a really nice cloud. Now, before we actually do it, I'm going to go and put a different color material, a different color washcloth down underneath it, and that's going to help you see the cloud form a little bit better. All right, so now we're ready to go. I have a nice orange washcloth where we can see the clear bottle over it. We've got our alcohol inside. We've got our nice plug and our air pump that we're going to use to pump air inside. Now, you'll have to jockey this different ways for yourself depending on the kind of pump you have. What I'm going to do is I'm going to stand right over here and kind of with my left hand, I'm going to force this air pump against my duct tape here. And with my right hand, I'm going to grab the bicycle pump and just force air. How much air do you need in there? You just need to play around with it. Just kind of give it a good nice 5 or 6 pumps and really hold it on there. When you let go is when you'll see the cloud form. So here we go. I'm going to start pumping. 1, 2, 3, 4, 5, 6, 7. Okay, 1, 2, 3, let go. And look at what we have there. A very, very impressive cloud. Now what we have here, what you're seeing here is the water vapor inside the air that was inside of this bottle quickly condense into basically a cloud. That's what clouds are. They are water vapor that have come together and formed these masses that we can see in the sky, and they've condensed basically into little droplets that then form together. So notice we still have the cloud in there. Before it goes away completely, oh, look at this. I actually split my duct tape here. So we'll fix that. I want to show you what happens whenever we put more pressure back inside of it. So let me go ahead and quickly create a new duct tape plug. Put that here, put it right on top, and then put a hole right there. Now look what happens. You can still sort of see the cloud. Watch what happens when I pump it back up. Notice the cloud disappears. When I put pressure back into it, the cloud disappears. And then when I release the pressure, I've got another cloud form. Now, when we do these experiments, we really need to take a minute to try to understand what is going on here and why it works. All right, so how do clouds form is the first thing you have to ask yourself. Forget about what we did here. Clouds form in nature because we have a body of water. The sun hits it, the water evaporates, it goes into the sky, and when enough water makes it into the sky, they kind of come together and form masses of water vapor in the sky that have kind of condensed into little droplets, right? And those droplets, when they get big enough, they fall back to the earth as rain. So it's sort of like this cycle. The water comes down as rain, evaporation brings them back up to the sky, then they collect together, and then they fall down. But one thing that you may or may not have known is that whenever they make it back up into the sky, the higher you go in the atmosphere, the colder it gets, right? So the higher you go 1,000 feet, 2,000 feet, 10,000 feet, the higher you go, the colder it is. And in order to make water turn from vapor back to liquid, to condense it, you need to cool it off, right? That's something that we learn about when we talk about evaporation and condensation. And that's how rain clouds form. The water goes up, it gets cold up there, it condenses out into these droplets, and then they fall back down. And it's happening because it gets colder the higher that we go into the atmosphere. So being colder or cooling the water off, the water vapor off, is kind of important to make clouds, right? Now the other thing that you may not have known is that there's dust in the Earth's atmosphere all over the place. You go up in an airplane, you go walk outside, you can't see it, but there's always dust, always, always. And these clouds really love to form where there's dust. So when these droplets form in the atmosphere to make the clouds, they really like to form around dust particles that are just floating around in the air. So if you can find a place that has a nice bit of dust, invisible dust, but dust that's in the air, and you have all this water there that's cooling off, then you're going to get a nice big thundercloud really ready to rain, because it really makes the water have an easy job of condensing if they have some kind of like dust particle or something to kind of form on. And that's important as well. So the dust particles that we're talking about to make clouds easier to form, in our experiment, the alcohol takes the place of the dust particle. What we did is we put the alcohol, you can still see the alcohol in there. We put the alcohol in there because we know alcohol is going to evaporate really quickly. So we put the alcohol in here, we swirl it around the bottle, and eventually that alcohol starts to go into gas, to evaporate inside, or to go into vapor inside of this bottle. So inside this bottle is three things, basically, at this point when I cap it off. There's air in there. When I say air, I mean oxygen, nitrogen, the things that are in the air. There's water vapor, because there's always water vapor in the air, and no matter where you are. So there's water droplet, tiny, tiny invisible water molecules in the air, we call water vapor. And now we've also put these alcohol molecules, which are in the air as well. They're going to act like our seed particles, which are basically kind of like our dust, right? Okay, so that's what we did. Then we built this little duct tape thing just to be able to help us pump the air in there. And so what we did is we put this guy on the front of it. We held it on really tight with one arm while we pumped air in. Now let me ask you a question. What do you think happens when you pump air inside of a closed container? And you keep pushing air in, pushing air in, and pushing air in, and pushing air in, and pushing air in. Well, the pressure is going to increase. That's true. In fact, you can feel that when you use the bicycle pump. When you start pushing it, when you start doing it a few times, like pumping up a tire, it gets harder and harder to push that air in, right? But also, on top of being harder to push, you actually are slightly increasing the temperature of everything inside of here, of the air inside of here. You're raising the temperature a little bit when you force a lot of air in there. And that kind of makes sense, because all air is made of molecules, right? So if you put this on there and start forcing a lot of air in there, you're forcing these air molecules to hit each other. You're cramming them in, and you're kind of forcing them in there. Think about it in an elevator. You've got 25 people on an elevator. They're kind of bumping into each other, and it gets a little warm, right? Same thing with the air in here. So you're making it a little tiny bit warmer by cramming all this air in here, right? Now, at the moment you're ready to release it, you pull the tip off, and immediately all of that air that was in there, not all of it, but a lot of the air in there, immediately leaves through this hole, right? And as soon as it leaves, it basically cools off very, very quickly all of the air that's inside of this container. So one thing you may or may not have known is that any time you have a pressure in a container and you release that pressure quickly, it's going to cool off the remaining air that's inside that container very, very quickly. So we have high pressure. We made it a little bit warmer by pushing that air in there. We pop the end off. Immediately it escapes. All the molecules start to fly apart from each other and immediately cool down. And so we have all three things needed for a cloud. We have water vapor in there because we had air in there. We had the alcohol in there, which was kind of like the seed particles, almost like the dust particles, to help the cloud sort of have something to latch onto and form. And then we immediately cooled off the container. Instead of putting it in the freezer, we immediately released the pressure that cooled off all of the gas in the container, and you had that really nice, impressive cloud that formed. And this should also help explain why, when we put the bike pump back on the front of it and we pumped it back up with air, in other words, when we saw the cloud in there and then we pumped it with air again, the cloud slowly disappeared, because as soon as we start forcing air back in there, we're slowly increasing the temperature very slightly of everything in here. And then the water molecules, they go back into vapor. So the cloud disappears again. And then when you release the pressure, we lower the temperature again, and so on. In fact, you can't really figure this out until you do this for yourself, but whenever you actually pump it up and you release the pressure, what comes out of the front, like the cloud, if you kind of squeeze it and let the cloud come out, it's kind of cool. It feels a little bit cool. So we learned a lot in this section. We learned a tremendous amount in this section. We learned what a cloud is, how they form. We learned that we need to cool the water vapor off. We learned that we need to have some sort of dust, or in this case alcohol or something, for the water vapor to kind of latch onto and to kind of condense onto. And we learned that we need to basically have a cooling process in order to make the cloud form. And we did all of these three things in this bottle here quickly By releasing the pressure quickly, we lowered the temperature so much that the cloud instantly formed, and you can keep pumping it up and releasing the pressure over and over again and see this for yourself. Now, the only thing tricky in this experiment is figuring out usually a way to get your bike pump to actually fit on here. I did mine with duct tape. You can get a cork and a needle valve that sometimes works. And you might just have to kind of go to the hardware store and find a good way to connect your particular pump to it. But it's a very interesting experiment because everybody has a 2-liter bottle somewhere. Most people have a bike pump sitting around the garage, and most people have rubbing alcohol, and that's really all that's needed to do this experiment. But do make sure that you wear your safety glasses while you're pumping it up, because anytime you have pressure, you're pushing pressure into something, you want to make sure and have your safety glasses on during the times that you're actually pumping up your pressure. So go grab the materials, grab an adult, and go do this experiment. And you know, it's very impressive the first time you do it. So have fun with it and go learn about how clouds form.
Learn anything at mathandscience.com.
Today what we're going to do is what we call color changing milk. It doesn't sound very nice. It doesn't sound like it's an amazing experiment. But I guarantee you, if you do this at home, your jaw will kind of drop the first time you do it because it's really, really cool and it's really, really colorful looking. So everything for this experiment you probably already have in your house. The first thing you'll need is some kind of a plate to hold the mixture, right? So a paper plate is fine. You'll need a glass of milk, right? You will need some detergent, some dish soap. This is what we use in the kitchen counter and the sink. This is Dawn dish soap. You can use anything you like, but Dawn seems to work the best. You will need some food coloring, right? I have 4 different kinds here. They usually come four to a box, so any color works fine. You could use one color or all 4 colors. And then you will need also a cotton swab. So as you can see, everything we have here is something that most people probably have in their kitchen. So what I'm going to do is rearrange things here. Okay, now what we've done here is put our plate front and center and moved all of our other ingredients off to the side so we can see what happens. The first thing you want to do is put your milk in the plate. Now this milk, you can use really any kind of milk you want. There's nothing special about it. It works better with whole milk than it will work with 2% or fat-free milk, and you'll see why in just a minute. So use regular whole milk, and what you do is you just pour it into your plate until you get a nice little layer. Just a thin layer like that is really all you need. You can do a little bit more if you like, right? So make sure the entire bottom is covered. And what I like to do is give it a nice count to 10 or so, because what you really want is for this milk to not be moving at all. You want it to be completely motionless. So 5, 6, 7, 8, 9, 10. So it's been sitting there. We don't see any bubbles moving. The next thing you want to do is take your food coloring. Here I have, again, 4 different kinds of food coloring. It doesn't matter. You can use your favorite colors. And what we're going to do is put some drops. We're not going to spread them out. We're just going to kind of put some drops right on top of each other until we have a nice little red dot there. Here's blue. And you want to try to keep them separated. It'll make it a little bit more impressive as you'll see in just a moment. So we have the nice blue drop here. And then we're going to do the green drop right below. Like that. And then finally, I guess you could call this orange. And some food coloring kits may have different colors. It all works just fine. Really, the food coloring doesn't have anything to do with this experiment. The only reason we're putting food coloring in is so we can see what happens. Because milk is white, and so what's going to happen in a minute, the milk's going to start moving, we want to be able to see it. The next thing you want to do is take your Dawn dish soap, or whatever dish soap you have, and a cotton swab, and you want to dip it in there. You don't want a thick glob like that. You want to kind of work it off on the side until you have a good bit of soap there, but it's not dripping off. Okay, just like this. And then I want you to watch carefully as we actually place that inside of the milk. Watch carefully what happens at the moment we push it in. Here we go. 3, 2, 1, go. Look at that. The milk just kind of goes nuts. It completely spreads out. The green kind of completely intersected everything else, and it goes out. Let's go over here to the orange and touch the orange and see what happens. The orange flies everywhere. Okay? We'll go over here to the blue. The blue goes everywhere. So notice that as we're holding it here, the milk continues to move. You see it's continuing to move out from the point. We're not really moving the Q-tip. The Q-tip is staying motionless, but the milk is going. Now we can use the other side of the Q-tip to kind of get it fresh, see if we can get it going even better. And let's see what happens. We'll try this side over here, and that starts to move basically wherever you touch this Q-tip, the milk food coloring solution is going to tend to move out away from it. Now notice what's happening now. As I do it more and more, the effect is not as strong. See, when I first put that very first dot in there, things moved really, really rapidly. And now I can just grab a whole bunch of soap and just drop it in there, and not that much is happening. You can see it's not really doing the same thing. So you have to ask yourself as a scientist, how is this possible? How is this working? Well, obviously it's an interaction between the milk and the soap, right? Because the food coloring, we had the food coloring in with the milk and nothing happened. It just sat there. At the moment we dropped soap in there, it started radiating and going away from the point that we put the soap in there. We didn't have to move the soap around. We just stuck it in there and the milk just continually kind of shoots away from the point that we put it in there. And also, as we do it more and more and more and more and more, basically the experiment stops working. So that's kind of going to factor into what's going on here. What's happening is, this is an example of how soap really works. Notice, what do we use soap for? We use it when we have our hands that are greasy, maybe we've got some fat or something on our hands or some oil, and we want to get rid of it, right? So if you put that under water and you try to wash your hands without any soap, and you have really oily hands or fat hands or something on your hands that's really fattening, it's going to be difficult to get off. But you put a good quality dish soap on your hands, you rub them around really good, you put them under the sink, and you can actually start to feel your hands getting clean. What's happening there is this soap is not just a blue formula in the bottle, it's specially made to basically bond to those fat molecules and to those proteins that are in things like bacon grease and things that are in like oil and such like that. In this case, there's also fat inside the milk, and there's also proteins inside of the milk. That's one of the reasons why milk is so good for you, right? So what's happening whenever you wash your hands is that soap is bonding. It's actually connecting to the fat molecules, to the proteins. It's actually bonding to those molecules, and then the water is able to wash it away. So it kind of goes out there and it latches on to those molecules of the fats, and then the water actually is able to wash it away. In this case, we have a nice surface of milk, right, which has fats and proteins baked into the milk. That's just part of the milk. We put the food coloring there just so we can see what happens. And at the moment that we put the Q-tip into the solution, what happens is the soap starts bonding with those proteins, and it causes the milk to start to move, because what happens is those proteins and those fats, they you can sort of think of them as being agitated. They're bonding to that soap, they're moving away from the soap, and they start to swirl because of the chemical reaction with the soap, the same way that we're able to wash our hands clean. That's part of what's happening. The other part is that the soap actually breaks down the surface tension of the milk. So if you look carefully at a glass of water or at a glass of milk, you can kind of see that skin that's right on top. You can kind of dip your finger into the very top of a cup of milk or a glass of water, and you'll see the skin there on top. We call it the surface tension. That's just because of the water that's inside of the milk and the way that it bonds, right? And it creates that kind of skin. Soap immediately destroys that skin. That surface tension, and that's just because of the reaction that's going on as well there, the bonding that's going on. So there's two things. The surface tension is disrupted, and also the fats and the proteins start bonding with the soap. Those two things together cause the milk to physically start to move because of all the agitation going on and trying to bond with the soap that we're just putting in the water, and it starts to move away from the point that the soap is put, right? And that is the reason why the milk starts moving. The food coloring has nothing to do with it. Food coloring is mostly water. The only reason we put food coloring in is so we could actually see the swirling motion. So that's the science behind it. It's actually bonding the soap with the fats, and that's causing, along with the surface tension, causing the milk to start to get into motion, and that's why we see the nice colorful changes there. You can do this over and over and over again with a new batch of milk. However, notice that the experiment, the chemical reaction really stopped working. We can put it back in there. You can see it doesn't really do anything. The reason is that as the milk starts to mix, the soap that we're putting into the milk starts to mix with the body of milk that we have. So in other words, after the swirling continues for a while, the soap that we're putting in there gets mixed in with the milk, and then of course everything's already happened. So you can't just continue adding soap because all of the fats have already bonded, everything's already done, the surface tension's already not really the same as it was, and so the effect is not going to continue. So to do this experiment again, you'll need to get a fresh plate with fresh milk, with fresh soap, and fresh cotton swabs here to continue doing it. But it's really, really cool. Kids love it, and it's a great way to explain what basically a molecule is. The fact that you have these invisible things, they're bonding together, it's causing this motion, is a really neat way to learn about this stuff. I'm Jason with scienceandmath.com. Go grab these materials. It takes literally 5 minutes, and I promise you the first time you do it, I think you'll be surprised at what you see.
Learn anything at mathandscience.com.
In today's experiment, we're going to make what we call a density tower, or a tower of density. And what that means is we're going to take various liquids that you probably have around the house or that you can easily find at the grocery store, and we're going to put them in a container and watch that each of these layers are going to basically float on top of the layer below it and make a nice colorful tower that we can then use to kind of talk about things like density and buoyancy and floating in terms of what it means in science. So let's go ahead and do that. What you need for this experiment is, like I said, things that you'll probably have around your house. Get some vegetable oil, canola oil, corn oil works fine. You'll need a glass of some kind. In this case, I've got a glass jar, but a regular old glass will work fine. I've got some rubbing alcohol here. It's just regular rubbing alcohol that you get from the drugstore. Some water. I've got some Karo syrup here that you can get from the grocery store. Some regular old honey, again, just from the grocery store. Some red food coloring, and in here is just various different things that you find around the house. We're going to try to float and sink these things. I've got a dye here. I've got a pecan here, I've got a rock, I've got a few things in there. So this is sort of like whatever you can find around the house. So all of these liquids that we've listed here, they all have different densities. And density basically lets you know if something is going to float or sink. So if we're talking about water, which is usually, we talk about floating, we're thinking usually in terms of water. If something floats or sinks in water, all depends on its density, the material's density compared to the density of water. And in layman's terms, that basically means, is it heavier than water or is it lighter than water? So when we're talking about if a rock is going to float or not in terms of water, we're talking about how heavy is that rock compared to the same amount of water. If it's heavier than the equivalent amount of water that the rock occupies, then it's going to sink. If it's a piece of styrofoam, for instance, we know that that floats in water, then if the weight of that styrofoam is less than the same amount or same volume of water that it occupies, if it's lighter, then it's going to go ahead and float to the top. So that's what we talk about in terms of water, but that idea extends to any liquid, whether it's canola oil or honey or Karo syrup or whatever. So we're going to explore that here. Let me kind of move most of my materials over to the right-hand side, and we're going to we always do this. We wear our safety glasses and we're going to be safe about things. And what we're going to do before we do anything first is we're going to put our plate here that we're going to work on, because we're going to be dealing with liquids, so we just want to make sure we have something just to catch any spills. Now, one of the liquids here, notice some of these liquids are clear and some of them aren't. For instance, rubbing alcohol. It looks a lot like water, but you know it's not water, it's alcohol. So we want to make it visible. We want to be able to see it if it floats or sinks. So what we're going to do before I do anything else is just put some alcohol into the cup here. And I'm going to put some red food coloring in it. The only reason I'm putting the food coloring in the alcohol is just so we can see it. So we'll go ahead and be generous. We want it to show up. So we'll put, probably 3 or 4 drops, something of that nature on top of, on there. And we'll just kind of stir it up. So now we have a nice crimson color there. So this is not Kool-Aid though, this is alcohol. And we'll see how that reacts, or if it floats or if it sinks on top of the other liquid layers. Now, of everything here, honey actually is the most dense. And that means that once everything is all said and done, honey is going to be at the very bottom. And kind of think about it, if you've ever held a jug of honey and even compared it to like a jug of water of the same size, the honey is heavier. So that's actually going to go on the bottom. So what you want to do is literally just squeeze it on in there. And the thickness of your layers really is up to you. It doesn't really matter. But you want to have them thick enough so that you can see the end result. Something like that. You can see very clearly that you've got a nice layer of honey there, maybe a little bit more, because this is the bottom layer and I want to make sure you can see everything. So we'll go a little bit more and give ourselves some honey. Now, of everything else we have, the next lower density substance that we have is actually this Karo syrup. It kind of has the consistency of honey. It's kind of thick, like you can see it kind of coating the the jar here as I slosh it around. And as things go, if you were to measure the density of this, the highest density would be the honey, the next guy on the list would be the Karo syrup. Now when you're putting the next layers on, you need to kind of do it carefully. Don't just dump it in there super fast, because even though everything's going to balance out in the end and start floating appropriately, if you kind of do it too fast, you might wait a long time for it to settle. So for the Karo syrup, we want to go ahead and just very gently and gingerly kind of add that in there. So you can see it's kind of clear, and it just goes in, and you'll start to see it float on top of the honey layer. Now you have to look carefully though, because the honey is already kind of transparent. It's got an amber color to it. The Karo syrup, notice I got light Karo syrup. When you buy Karo syrup, you can buy it as a light version or as a dark version. And in order to be able to see it easily, you really want to try to get the light version of the Karo syrup. So let me just do a little bit more here. I think we've almost got enough Karo syrup in the container. That's about right. All right, so there's Karo syrup. Okay, now if you look carefully, what we have already, the Karo syrup is floating on top of the honey. Now what that proves to you is that it's less dense than honey. If we want to find out if something floats or sinks, we compare it to what we're pouring it on top of. So here we have honey at the bottom. Believe me, if these two things were both water or both of the same density, they would just mix into one substance. But since this guy has a nice distinguished layer on top, then it basically proves that it's floating on top and has a less density than the honey that's below it. Now the next thing we want to do is go and work with regular old water, because as we go in order, this is going to have a slightly lower density than the Karo syrup, so it's going to float on that Karo syrup. But because the Karo syrup is clear and the water is also clear, if we pour it in there, it's going to be really hard to see the layers. So what we're going to do is get our water here in our little measuring cup, and let's put some food coloring in that just so we can see the different layers. So I'm going to choose green here, just so I don't have anything else green in this experiment. I'm going to put a couple of drops to make it nice and vibrant. Okay, and we'll just stir that around. So we have a nice deep green color, which will show up nicely against it. Now actually I don't want it to be quite that green. I want to be able to see through it nicely, so I'm going to add a little bit of additional water to it just to lighten that color up more than anything else. I'm not going to use all this water. I'm just doing that to make the green color a little bit lighter. All right, and so what we're going to do is pour it in. Now again, you got to be careful. You don't want to dump it in there, because then it'll start mixing. It'll take a long time to settle out. So actually, if you have like a turkey baster or something where you can kind of like gently put it in, that would be even better. But in this case, we'll just gently pour it on top. And you should be able to see it start to form a layer right on top of that clear Karo syrup. And notice why we colored it green now, so we can actually see it very clearly. All right, that's good. So now we have three nice layers. We have our honey, we have our Karo syrup, and notice this nice green water that we've colored is floating right on top of the Karo syrup. If you gently tilt your bottle, you'll see all the layers move. So everything's floating on top. They're not mixing together. All right, next, we all know that oil likes to float on top of water. And so this is water, and here's oil. I'm not going to color the oil because we've colored the water. Everything will stand out. And again, we want to be careful. We don't want to go nuts. We want to just sort of gently pour it in there, because we don't want too many bubbles to form. It's kind of inevitable whenever you deal with oil and water, you're going to get bubbling. But they will eventually go away. If you set this on the counter for an hour or so, then all of these bubbles will completely disappear. In fact, even over the next few minutes, they'll sort of disappear. So let's go ahead and put that in there. I think that's a pretty good layer, maybe a little bit more, like this. Okay, so what we've shown here is oil is less dense than water because it's floating. That means for the same amount of the stuff, for the same volume of water, the oil actually weighs less, so that's why it floats. Now what we want to do next is we want to pour our alcohol, which is our rubbing alcohol, in there, and we're going to transfer it to a measuring cup so that we can have a nice pour spout and get it in there without getting it all over everything. Now what you can see after we poured the alcohol in is it kind of dove down deep, and then it started to form these bubbles, and notice how it started to come back to the top. So you can clearly see that we have a red layer on the top. That's the alcohol that we colored red. So our 5 layers are, in order of increasing density, we have an alcohol layer, we have an oil layer, and then we have the green water layer, and then we have Karo syrup, and then we have honey. And notice the boundaries are very, very distinct and very, differentiated from one another. Now notice, again, we have bubbles all throughout this container. If you were to let this sit on the counter for 30 or 40 minutes, these bubbles would basically all bubble up into their appropriate place, and they would basically disappear. But what it shows you is this is your tower of density. It shows you that things can float on top of one another depending on their densities. And you kind of have intuitive understanding of that. Alcohol is real thin, it evaporates quickly, and it just doesn't feel like there's much there. And then you have oil, which is a little bit thicker and heavier. And then you have water, which is even heavier. And then you have your syrups, like your Karo syrup and your honey. Now, if you notice carefully, what we see has happened is we have a nice red layer of alcohol here, but we also have kind of some of this red that's kind of bled down here near our water layer. Well, what's happened there is, what do you think food coloring is made of? Food coloring is some kind of coloring, and it's mixed with water. When you squirt the food coloring out, it's mostly water. So the water in there, some of it has descended down and kind of mixed in with our water layer. So really, in our tower of density, we have honey, we have Karo syrup, and our water layer is right here. It's got the green stuff, and it's got a little bit of red as well, because that's some of the food coloring made its way down there. And then we have our oil, and then we have our red alcohol here as well. If we would have just put the alcohol in without it being red, without coloring it first, it would be a real difficult time to see that. All right, now we get to have a little bit of fun. Let's go ahead and put this on the white sheet of paper, and let's see if we can figure out what's going to happen to some of these things. So here is a rock. I imagine a rock's going to sink, but the question is, where is the rock going to stop? What layer is it going to stop at? Is it going to go all the way down to the water and kind of just go below that? Is it going to go all the way to the bottom? Or is it just going to stop somewhere in the middle? Let's find out. So if we gently drop this rock in, of course it's going to mix everything up along the way. Where is it going to stop? It made it through the water layer, and it's gone into the honey layer. It looks like it's going to the very bottom. Okay, so this is our water layer here, which is kind of the greenish with this blackish stuff here. That's our water layer. So it looks like it made it all the way to the bottom. What does that mean? That means that that rock, the density of that rock, is greater than honey. It means if you look at the same amount of honey that was occupied by the space of that rock and compare them together, the rock weighs more. And that's why the rock goes down there. And it kind of mixes things up along the way. Let's take a die. This is a regular old die that you get out of a board game. Let's gently drop it in and see where it goes. The dye goes through the alcohol, it goes through the oil, it goes through the water, it's into the Karo syrup, and let's just see if it settles on top of the honey or if it continues down to fall on top of the rock. And it looks like it's going into the honey on its way to the bottom of the container. Okay, so it looks like it's more dense than the honey. It looks like it's kind of wanting to stop, but it's going a little bit deeper. What about something like this pecan? This is something that everybody has handy. We'll drop pecan in. It's heavier than the alcohol, heavier than the oil, but as soon as the pecan gets to the water layer, which is this kind of blackish layer right here with the food coloring, it actually floats there. So that means basically whatever you drop in here, it's going to stop right at the point where it hits the liquid that it floats on top of. Pecans float on water because they're slightly less dense than water, and it sinks through these other layers in order to get there. Okay? What else do we have? Here is a piece of wood. Let's see what a piece of wood does. Piece of wood actually stays right in the top of the container. It doesn't actually go anywhere, it just stays right on top. So this wood is actually less dense than even the alcohol. Not even dense enough to go down any farther. Let's try this bottle cap. Actually, let's try this plastic cap. Just drop that in there and see where that goes. And I'll use my screw to actually kind of push it down, give it a little head start. And it looks like the bottle cap sinks past the alcohol layer but starts to float in the oil. So the bottle cap is floating on top of the oil. That means that the bottle cap is more dense than the alcohol, but not as dense as the oil. So it's less dense than the oil, so it floats there. The screw, I'm going to bet that it goes to the bottom. Let's check it out. It goes all the way straight to the bottom of the container. And you can see that right there. It goes straight to the bottom of the container. That kind of makes sense. What else do we have? And actually, it looks like the bottle cap descended a little bit farther. It was just really slow moving. It looks like it floats on top of the water. I have a red bean here. Drop the red bean in here. That goes through the water, and the red bean looks like it floats on top of the Karo syrup, at least for right now. So it went down through and it floats on top of the Karo syrup. What about a straw? Regular old straw, like a drinking straw. Looks like it goes through the alcohol layer, and at least for now, it looks like it is right on top of the oil. Anyway, you can have fun dropping various things in there. I have a paper clip here. Let's see where the paper clip goes. Paper clip shoots down, goes into the Karo syrup. Let's see if the paper clip stops on top of the honey or not. Let me turn that here like this. Looks like the paper clip might stop on top of the honey there. It just depends. Sometimes whenever it hits the really thick layers, it just takes time to settle through. So that is what we call a tower of density, or a density tower. Basically what we're doing is finding different liquids from around the house and choosing them and stacking them on top of each other so we can see the different layers, and that's telling us how dense each of these liquids basically are. The least density item, liquid's going to be at the top, and the most dense is going to be at the bottom. Once you've constructed your density tower, you can start dropping various things around the house. Make sure you choose things you don't mind if they get a little wet or a little sticky. And depending on how dense they are, that's where they're going to stop and start to float. So they'll go down to the level, to the liquid level where they begin to float. And it all depends on the relative density. I'm Jason with scienceandmath.com. I hope you've enjoyed this experiment. It's very simple to do, very easy to find materials. Just need to make sure and get permission before you start mixing things together to make sure it's all safe, which this all is. And then you can go have fun learning about density, learning about buoyancy, and using the knowledge of science to predict how this sort of thing is going to work.
Learn anything at mathandscience.com.